Good morning, everyone. So it's a pleasure to be here, opening basically the ICBC. Starting with this tutorial, that the main idea here is to give an overview of blockchain since from its evolution and its basics, and the idea on how you, mainly how you decide on whether you can use blockchain, whether you have a case in which blockchain is really useful or not. And also going from smart contracts, that we will overview a bit on how you can, some best practices on how you can make a smart contract more efficient, and take a look on some examples of smart contract security here in practice that we're going to show. So I'm here, my name is Bruno from the University of Zurich, and those are the persons that we work in our group, so we can have this material to show here. And the idea here mainly go in these three stages. In the first part here we have the blockchain motivation mainly, timeline and basics, and then we go to the consensus mechanisms and then management aspects that we see basically the process on the adoption of blockchain. The idea is to see basically the properties and first the evolution of the blockchain on how we get to the stage, to the point that we have now. Then the consensus mechanism, that's mostly the basics, the heart of the blockchain, to the decision process. And then we go to the smart contracts process that we have the definition of smart contracts and then the best practices on how you should develop your smart contract. And then we focus on the security examples. And then we close with the discussion of challenges and considerations. Mostly here, we have this timeline of blockchain in which we have the events here since the proposal of Bitcoin that defined, that was the first work on blockchain that opened the eye to the blockchain. So first, the proposal of of Bitcoin for, this is in 2008. And then we have here a timeline for the public perception as well, in which we can see how the public perception evolves through the stages. And for example, here in 2010, we have probably now, as of today, the most expensive, too expensive slices of pizza. That was the first time someone bought something using Bitcoin. And this evolved until February 2011, when you have, for the first time, one Bitcoin having the same price as $1. And this started to open the eyes of a lot of people, to drag a lot of attention to Bitcoin. And since then, the public perception started to increase a lot. So there's also here, there's something here very interesting that can be used beyond only a cryptocurrency. And only as a remark, a point here in March 2013, you have a market capitalization of $1 billion. So this is already a very interesting, using the investment, the capitalization as a metric to feel how the public perception on Bitcoins, on cryptocurrencies, were at this point in time. And on this era, it's called the blockchain 2.0, we have basically unlocking the potential of blockchain with the proposal of Ethereum. So basically the idea here with the proposal of smart contracts was to execute random code, arbitrary code on the blockchain, using the infrastructure as a support for decentralized apps. And this, we have still the growth of cryptocurrencies still in parallel with this era. And for instance, we have one attack in February 2014 on the Mt. Gox, this exchange. And important to notice here that even though a lot of money was hacked on the Mt. Gox, it was not an issue of blockchain. So the code of blockchain, Bitcoin to be specific, remains safe, secure as of today. And the issue was only on the exchange. So the code is safe, so to say. And one example of how we should take in consideration best practices on developing smart contracts was the DAO hack. That by exploiting one mistake in the smart contract, hackers were able to draw from the contract $50 million US. And these start to drag a lot of attention on how you should use best practice, how you should review your smart contract code and pay attention to those lines and have a very simple contract being deployed on the smart contract. If we go forward, basically, we have this era of blockchain 3.0 that basically a lot of people started to see that you can really decentralize applications using blockchain. And then it's the idea of this production stage. You started a lot of applications that start to appear, and you can see basically growing as of today, you have a very large number of applications being deployed and for all sorts of areas. And one of the issues that we started to take, to need to pay attention, if all those applications really make sense in practice, are those applications only exploiting the hype of blockchain? So this is something that we, from the community, from the research community, need to pay attention on the fundamentals to see whether something makes sense or not, or it's only a hype, a commercial hype. And also on this era, you started to have the first problems with scalability and performance issues. So you start to use for a lot of applications, those applications have needs, and the blockchain is limited in the sense of, if you take in contrast, traditional databases. So there's a need for performance, and this also pushes on one side, on the research side, to look for new consensus protocols in order to make the blockchain increase the number of transactions per second to follow the application demands. Also, the need for storage, and this also pushes the usage for off-chain storage tools. And as of today, we can see that they call this blockchain 4.0 era is basically have a really effective integration of these various applications proposed in the 3.0 area and having an effective integration with industry. Now, as of today, we can say that we have many blockchain projects being proposed, and what you have is different and decentralized and disconnected blockchains. So you have very application-specific blockchains which are not necessarily talking to each other. And we have many proposals, for instance, this Cosmos project, Internet of Blockchains, to have points of interconnection, interoperability. It's an issue that started to appear in this stage that you need to have your application really being effective and talking, for instance, with your ERP or another blockchain. So this summarizes those eras, those 4 eras, so to say. And the thing that we have that all of those eras are running in parallel as of today. And we have from the first one, of course, was Bitcoin, unlocking basically the proposal of the blockchain itself. Then you have Ethereum with the smart contracts, unlocking the potential of blockchain with Solidity. And then we have the explosion of these various decentralized applications, and in the last one, trying to make all of those effective in industry. All of those are running in parallel in those various areas of application that we have, and basically they need to make those efficient, to make those secure from the code that is running on the blockchain itself. So there is this need that we need to take a look as of community. So basically, the driving questions that we have here is how and under which conditions to have to use blockchain. This is either from a developer perspective that you are starting to develop now your applications to use these in your research project, or also from an investor point of view, which project makes sense, which is only a hype. And this also needs to be taken in consideration. And one question, is there a right or wrong? A roadmap, if possible, it's something that we need to see. There is no simple answer, because you not only need to have in mind the properties of the blockchain, but you also need to have in mind the application needs, the application demands, the trade-offs that you can have, and balance this in order to get to an answer. So there is no straightforward answer. And basically, this is what you need to do, what my application needs, what are the application requirements in terms of performance, scalability, security, also interoperability. On the blockchain, you have now many different types of blockchains in which you can use to deploy your contract, to use in your application, what those blockchain projects can offer in terms of the application needs, and then perhaps you can propose your new blockchain 5.0 application. So with those driving questions, that's the idea of this talk. Basically, I will present the basics here, and then the consensus mechanism, and then we go to to analyze this decision process. On the basics here, we'll go a bit fast on the basics because blockchain conference. And here we have very interesting on this definition here. It's a decentralized digital ledger that transparently and permanently records blocks of transactions across computers based on a consensus algorithm without modifying the subsequent blocks. Some people in the academia would even go further and say that only public blockchains are real to the definition. So, because when we start to see how the different blockchains are deployed, we have different ways in which we show the next slide. But some more fundamental people just say that the blockchain should necessarily be public, which means that everyone should interact, everyone that has access to the internet could interact, either to read or write on the blockchain. This is what we have more or less defined on this figure here. We have mainly the case for public and permissionless blockchain on the upper hand right corner, in which is the case for cryptocurrencies, mostly that everyone that has access can interact, can deploy, not can deploy, but can interact with the blockchain. One second case would be the public permissioned, meaning that the readability, everyone can read what is in the blockchain, but not everyone can write. And for instance, this is the case for e-government cases on identity, authentication. And if you go forward here, the private permissionless means that you start to close the reading rights to a community. And inside this community, everyone could participate, which is more or less the case for supply chain, in a very general sense, in which only the members of the supply chain can interact, can see what is there, but not the community from not participating of this blockchain. And then on the last quarter there, we have the private permissioned block case, which unfortunately we can see some cases, but it's very hard to justify the use of blockchain on a private permissioned case, because the meaning is that you are closing the reading and the writing access, and it's a very clear case that you could use a traditional database, and using blockchain you're making things more complicated here. So block is mainly very similar to a packet. We have a header and a data that's mostly a set of transactions. What is interesting here is that we have this Merkle tree infrastructure that is basically what can ensure you the integrity. So each block has a hash and also pointer to the hash of the previous block, and each transaction has also a hash. And basically, the Merkle tree here, what it does is to take the hash of each transaction, and then you construct a tree here. If I can show, you construct a tree here with each hash, and then you move forward, and then until you have a Merkle tree hash. For this Merkle tree hash, you hash with the previous block, and then you get to a single hash of the block, meaning that if you change, or if you try to remove any transaction from this block, the block hash will not be the same. Which this in practice ensures you the immutability of the blockchain. You imagine that you want to remove a transaction. Basically, if you do this, the hash will not be the same, and then you start, from this point on, you create a fork, which will not validated by the other miners in your blockchain. So basically, what you're doing here is to ensure integrity. And if we move forward here as well, how transactions are stored in a block. So imagine that we have here Alice and Bob. Alice wants to send a message, hello world, to Bob. And this transaction is sent to the broadcast, and then this goes to the transaction pool or mempool. And then on the mempool, this will have to be analyzed for the miners. The miners will have to check the incentives to see which transactions they collect to store in the blockchain. Supposing that Eve and Dave are miners, they gather all those transactions to try to generate a candidate block. They have to, for the case of proof of work, they solve mathematical proof that is basically trying to solve target a partial collision of hashes that they try to find a hash that is below, that's above the target of zeros. Once they find a block, they generate this candidate block, and this is dependent on the blockchain. Okay, so we have seen very quickly here on the basics, but then we go to this main point that is the blockchain consensus. Basically, how you decide which you have an agreement on this, those different nodes, how you decide which is the next block to be appended and who is entitled to generate this block. Also called distributed consensus algorithms, and you have these 4 key characteristics. Basically, you need to have an uniform agreement. No, 2 nodes decide differently. You have integrity. The node can only decide once. You can have a node, for instance, a miner deciding twice on which transactions are going to be in the block. Validity and also determination. So these are the 4 key elements that you need to have in the distributed consensus algorithm. Basically, if you have a group of nodes, a set of proposals, every non-failing node will eventually decide on a single proposal. So you don't have nodes deciding twice. And all non-failing nodes will decide on the same proposal X. So definition of consensus algorithm, and then we move forward with an overview here of how the different areas of the consensus mechanisms are in the blockchain. So we have the first one, this is the Byzantine Classic here, that are mainly the Byzantine Classics, the Byzantine fault tolerance, and also the two-phase commit. There's mostly dealing with crash failure algorithms. And then this evolved mostly in Bitcoin with the decentralization. So instead of you relying on a node, a super node that you say that this node will be the one that will decide which transactions will be in the blockchain, then you have an election process. So now your miner has to solve a difficult problem to be elected, to be entitled to to decide on which is the next block. And what we can see on this evolution from 2 to 3 is starting to propose different consensus algorithms to cope with the needs for performance and also the scalability. So you can have now hybrid consensus based on the idea that if you have a community on your supply chain and supply chain is using a private permissionless blockchain, you can use a different consensus algorithm for this community, but you can also have another connection with your cryptocurrency, doing payments on the supply chain using a public permissionless. So the idea is that now you can have more, you can be connected to more than one blockchain, and you can have hybrid commitments. And you can have the hybrid sharding on the number 4. With those multiple communities being available, you start to have the need to interconnect, to have a way in which those communities are interoperable, and which is the idea for those interoperability proposals, interoperability blockchains, that you basically what you are doing is to interconnect to different blockchains. And there are different approaches in which you can do that. Using, for instance, a notary, you need to trust a party to say something happened on the chain A, and this will reflect on some event on the chain B. You can have another chain, a virtual chain, taking a look on what happened on a single chain and doing transaction on a single chain, and so on. The idea of classical consensus mechanism here is starting with the Byzantine fault tolerance, is that first, initially, that you have to support the crash failure model. So if you have a node failing, you have distributing or the state of one node to many nodes. But this assuming that you have honest nodes failure. But you can also have the case in which nodes are actually acting maliciously in the network. But assuming here this example of the BFT general problem, supposing that you have Rome, and the different cities in Rome need to attack, the different cities surrounding Rome need to attack Rome. If all of them, they would be successful, for instance, if all of them attack at the same time, but they have this issue of communicating to each other. Basically, and you also don't know if the general, for instance, could attack a single city, they could act in a random way. The issue here is that they would have to communicate to act at the same time, to attack Rome. Or either they commit and do it at the same time, or they do it in different ways. So this is a Byzantine fault tolerance problem that you can have a mapping. And for example, you have the Byzantine, here is the capacity of a system to handle or survive to unreliable situations. And you have an implementation of this, that is the PBFT, the practical Byzantine fault tolerance, that can assume a portion of nodes acting maliciously, being dishonest. And this is done in 3 steps, basically on the prepare, prepare, and commit. We start with a client sending a request to invoke a service, and basically starting to send a lot of transactions. And then the primary leader has to, a node acting as a leader, you take those transactions and send to the replicas. So, and then the replicas would execute this and come back with an answer to the leader, which will then reply to the client. PBFT is implemented on Hyperledger. There is a trade-off on PBFT. The first one, of course, obviously you need to trust on those elected leaders, those elected nodes, and this is limiting in a sense that you cannot apply to all cases. You have, which is one of the reasons why you can use this in supply chain, for instance, in which you can trust a set of nodes, and then you can switch the consensus mechanism. Another example, the XFT and also the Honey Badger. And then we move forward to from the classical consensus mechanism to the elected leader models, in which you can now elect a leader. Instead of defining a leader, you can have different types of consensus, being the most famous one, the proof of work. Delegated proof of stake, the proof of stake, the proof of capacity, you have proof of deposit, proof of many different types. And a variation, for instance, the proof of stake is the proof of authority. Now that you can define authorities in your network that will act more or less as leaders in the PBFT, that will now be able to be entitled to sign blocks. And many different other variations of this is incomplete. You have now many variations of consensus mechanism being proposed. In the proof of work, basically what you take when a set of transactions becomes available here, you take the transactions and also announce an arbitrary number that you can only use once, and also the other information that can depend on the implementation of the proof of work algorithm. And then you check you calculate the hash of the new block. And for this, you have basically to check whether the target hash that you need to achieve, it's above or below target. If it's above the target, means that another miner could have found this hash and you have to try again. Or if it's below the target, then you won the lottery. The lottery, so to say, because you actually need to do this partial collision of hashes to find those first number of zeros that says that you could solve this problem and this hash is valid. Which is for example. This can be mapped as a distributed game in which you have to find this number of hashes here. For instance, you start with 1 0 and this takes nanoseconds until, and then you start to increase the number of hashes, increasing the difficulty of the hash, and this becomes way more difficult to find a hash with this number of zeros in the input. And this difficulty can be adjusted. For instance, in Ethereum, you have a block time, and if the hashes are starting to be found below this time, the protocol automatically adjusts the difficulty, increasing the number of zeros that you need to find, so in a way that you can reach the defined block time in the blockchain. And if we move forward here, a variation will be the proof of stake, in which you don't need to solve a difficult problem on the blockchain. You can now mine blocks defined on what are your stake on the network. So basically, you have a number of coins at stake, and what you do, if A mines the block, considering that A and H has a high number of stake, it can put its coins at stake and be entitled to create the next block on the blockchain. H mine the blocks, and so on. The idea here is that now you don't need to have the computationally intensive work of proof of work to decide on what is the next leader to mine the blocks. But now you can base it on the coins that you have at stake to decide on what is the next one, to decide which is the next block. But on this, we have an issue that is the nothing at stake issue here. That's basically when you don't burn an external resource, you have the issue that you can now start to create forks. And then you have the issue of the double spending. When you don't have to, for instance, to burn an external resource. In this case here, you have one very clear case of double spending, that this Vero sends scripts to the exchange, buy Bitcoin at the exchange, sends off, and the chain dies shortly after that. In the meanwhile, you could do this double spending of your coins, and then you put all of this, your staking power again, and while the fork was created, you are able to expand your coins twice. So when it's costless basically to mine a block, you have this issue that you can just put your money at stake and then you can create forks. And the idea that you could bind your money at stake with some cryptocurrency, for instance with Bitcoin, in which you have a computational effort there. Moving forward, we have proof of authority, where there is a variation of proof of stake here. It's a modified form of proof of stake, that now you take the identity of a node as to perform the role of a stake. So you're saying that this node here is the one that is entitled to write blocks in the blockchain. And you have those authorities being implemented with the click that requires at least 50% of your signers in the network to be honest. And then the authorities can sign the blocks, at least for the click implementation in a round-robin fashion. You can have A, D, E, and H as authorities. And they will be deciding on which are the next authorities, next ones to mine block. For all of those different consensus and protocols, you have to analyze basically what are the application needs, because not for all applications you can use those different consensus, and also for the blockchain type of deployment. In this third stage here, we have the classical ones, and then ones that you can elect or select the leader. And also you can have an hybrid consensus, meaning that your node, your application can be connected to more than one blockchain. Taking the case here, you can have your application being connected to one Ethereum network using proof of work, and also on Ethereum using proof of authority. And the idea that your node can support both at the same time. And you can have basically one supply chain on the proof of authority in which you know which are the authorities entitled to write information in the blockchain, and you can do payments on another parallel blockchain using proof of work. And the idea with the hybrid sharding here as well is that you can have now communities, and those communities can talk between each other. So you can have the idea of this notion of interoperability, the cross-chain communications. And many of the projects are also evolving on this way, especially on the 4.0 era, in which you have the necessity to make all of those different blockchain proposals being effective, really effective on industry. Yep, in this example here, we have proof of work Ethereum trying to communicate with an Hyperledger, and they do not communicate directly, and then you need another external approach to make those communication, to make this communication. And taking a comparison here of the consensus mechanisms, we have basically considering the security level and also scalability. You have, of course, different properties, but it's very important to analyze when you can use those consensus mechanisms. Proof of work, for instance, you have on one side you have the very high energy consumption, the need to solve a hard mathematical proof to be entitled to mine a block, but then this ensures you basically more security, in the sense that you don't need now to trust on a node as if BFT or proof of authority. You don't need to rely on a node to decide which is the next block, but then this is distributed. From one side, you are gaining a bit more of trust. On the other side, you are leaving performance and scalability aside. And then we move here to the blockchain adoption process. That's now we saw basically how blockchain evolved on those different timelines, some of the properties and the consensus. And the idea is to decide basically when to use and how to use blockchain. This is not a trivial task. As of today, we have 2,100 or 200, something around this on CoinMarketCap. Cryptocurrencies, and not only cryptocurrencies, but you have also many other projects available. And then there's a myriad of parameters that you need to take in consideration. For instance, if cryptocurrency, you can take a view on what is the investment, what is the capitalization of this cryptocurrency, what is the community involvement. If you are starting a research project, it's very important that you have support to start to learn how to code your smart contract. And full node, the miners geolocalization, politics, for instance, if all of those nodes are deployed in a country that you don't know, what are the regulations, what are the impacts of those regulations in your business, then this is something that can be, this is definitely negative to your business. And also the security, you have mainly to look on the consensus mechanism, which is the consensus mechanism being deployed, what are the possible attack vectors, many things that you need to take a look to decide. There have been some works on this area already. The first one to point here was a blog post of Gideon Greenspan that named it Avoiding the Pointless Blockchain Project. He named it 8 points in which you need to take a look, to consider, to determine whether you have a blockchain case or not. Based on this, Carl Wurst and Arthur Gervais did a very nice work defining clear methodology, whether do you need to help you to answer this question, do you need a blockchain or not? We analyzed also the application trade-offs, basically what you gain, what you lose, considering one kind of application. And for this, it's important to have in mind always the different types of deployment in face of your application needs. If whether it's a public permissionless, case of cryptocurrency, private permissionless, case that you close the readability, public permissioned, or a case that is clearly that you don't need to use a blockchain. Going here to the points of Gideon Greenspan, he basically defined those 8 points, but those last 2 are mostly recommendations. The first thing that you need to observe, very straightforward, database. Do you need to store state? Are those multiple writers in the blockchain? One thing, if you have only one writer, you can use a traditional database. You have multiple writers, then you can start, you can keep going for the next points to observe. The third one is the absence of trust. If you can trust one of those nodes, means that you can centralize, and then using a blockchain might not be that good. If you can trust a node, you can use basically this decentralized, distributed database. Another point is that if you need disintermediation, for not all the cases you need to do this disintermediation, the transaction interaction, and also set the rules. You need to have clear rules applied to all of those writers. If you have, for instance, different roles applied to different writers, traditional databases have way more maturity, and then you could use these in your project. And also those 2 recommendations basically pick your validations. Need to have a very well-defined scheme of trust in which you know who is going to write. Back your assets. Basically, the first concern here with the translation of digital assets into the real world. The first concern, what is the value of a cryptocurrency? And what is the value of these translating these into the real world? So the first 2 recommendations from the points that you need to observe. And then on this work here, it's a very nice, very clear, straightforward method in which you can see on how, whether you need to use a blockchain or not. The first one, do you need to store state? If no, if you don't need to store state, then you don't need a blockchain at all. If yes, then you need to check whether you need you have multiple writers. If you have multiple writers, then okay, you can go forward. If not, then you don't need a blockchain. Moving forward, do you have any third trusted party that you can trust to have your data, to send your data and mine those data, store in the blockchain? If you have, then it's a case that you probably don't need blockchain, but if you have, then you move forward and ask if all the writers are known. If not all the writers are known, it's the case that you have a permissionless blockchain, case for a cryptocurrency, for instance. If you have that all of the writers, if you know all the writers and all of those writers are trusted, again, you trust everyone in your network, then you don't need a blockchain for this case. If no, if all of the writers are known, and then you don't trust all of those writers, then you need to check whether you need a public verifiability or not. Public verifiability, if you have a public verifiability, is the case for public permissioned one. For instance, the case in a governmental case for identity, in which you need to have one identity issuing those identities, and those identities need to be visible. Or you can have a private permissioned blockchain. So basically, this is a very clear schema in which you can decide on whether you need to use a blockchain or not. They also defined, started to take a look on some of the parameters in contrast to the different types of blockchain, analyzing the difference between them. One of the first attempts to look into the application needs in contrast to what the different types of blockchain are offering you. Basically, if you need throughput in a permissionless blockchain, this is low, and you can take a look at permissioned. You can change the consensus mechanism, for instance, to use PBFT, and can have a high throughput in terms of transactions per second, but it's not as close as centralized databases. In terms of latency as well, number of readers, number of writers, number of untrusted writers. So different parameters that also need to be observed while deploying your application and choosing which type of blockchain do you need, or no blockchain at all. One thing that we did is to analyze the blockchain characteristics, and taking the applications and analyzing the trade-offs, trying to define a line for use cases in contrast with if you need performance versus reliability, if you need confidentiality versus transparency. For some of the cases, confidentiality is a very important requirement, in which basically if you fill all of those steps in the worst, for instance, and you still, confidentiality is something important, then blockchain isn't an issue. If you have distributed versus centralized control, also concerning trust, the issue with limited storage on the blockchain, the need to use off-chain storage, and how to make to make your application with the demands of your application being effective in the real world, for instance. You have the issue with unknown regulations, your applications being deployed in different countries, different regulations. You need to be aware of the compliance of those different places in which your miners are. Also, with the lack of standards, if you consider the case of blockchain 4.0 and the need to make those different blockchains to communicate, you basically don't have standards. Those blockchains are implemented in different ways, and they do not communicate. And standards, it's something that we need as a community also to evolve, to have a more clear, well-defined standards. One example here for distributed and centralized control is that you can have those multiple possibilities that being deployed at the same time. So your application can be either connected to a public community, to a consortium community, and also use a private database. And you need to analyze all of those properties at the same time to decide on whether you trust on node A, B, or C, or no trust at all, and then you use an Ethereum, for instance, with proof of work. So you have many parameters, characteristics to be observed, to be analyzed, in contrast to the different types of blockchains that you have available. If we map here the trade-offs to the blockchain types, we have basically concerning performance, reliability, the control, and the transparency. In the public permissionless, for instance, you have world visibility. The control is mostly for proof of work here in this example in an election process. So you don't know which is the node that is going to take the transactions and store those transactions in the blockchain. You have a full replication, So it means that the system is reliable in the sense that if one node fails, the information is distributed across the network. But also, for the same reason, it's slow. You have a time in which all of the network need to be in the same state, and if you have miners nodes spread across the globe, this is low because all of them need to be in the same state. If you have a public permission, it means that you can still have a role visibility, but now you have a selection process. You can define the nodes which are going to control the network, define the state of the network. You can have either a full or partial replication of data, and the performance is balanced between the proof of work and then between the private blockchains. In the private blockchain, you define basically those who are going to write. So you have a community visibility. You define a community, for instance, the supply chain, and the control is distributed. You have the validators in a selection process, full or partial, and it's intermediate, the performance. In a private one, you have a role-based visibility. You have those master nodes, the ones that are going to read. And decentralized on the trusted nodes, you can also have a full or partial replication using a master-slave mode, and it's fast in contrast with the other models. With this, we basically close this first part. I don't know if we have questions thus far. If not, we go to the smart contracts part and start to take a look on basically on the principles of smart contracts and also the best practices and the examples. Moving forward, basically, smart contract reside inside transactions here. For Bitcoins, also we have a smart contract, a very simple smart contract in contrast to the one on Ethereum, but you do have smart contracts basically able to refund transfer Bitcoins from A to B. Smart contracts is not something new. As we saw, this was proposed in 1996 by Nick Szabo, which states that smart contract is a computerized transaction protocol that executes in terms of a contract. And you have that basically that minimized the need for trusted intermediates. But at this point, the smart contract was not smart by itself because it needed the proper infrastructure to execute. So it was proposed in 96, but since then it was not used because it was missing the infrastructure to make it fully applicable, fully usable. And then they need the infrastructure, and then blockchain was the perfect infrastructure, so to say, to execute smart contracts, the ideal, which basically now you can have those contracts, especially in Ethereum, general purpose contracts, being executed in a decentralized way, in a way that is transferred to all the nodes in the network, and everyone can see what is being executed there. One of the issues that we observe is the legal relevance of coded general contracts. For instance, in Switzerland, those contracts has no legal validity at all. It's just code. Even though it's transparent, it's immutable, but the legal validity of those contracts is not, it's something on heavy discussion. Those are not considered valid, at least on Switzerland, I can say. And this is an issue. Code is the law, code is not the law. There are some works, especially from the legal community, analyzing the legal validity of smart contracts. And if we take here, move forward to an example of Ethereum and Solidity, we can have this very simple hello world contract, in which we basically, when you call hello, it will return you hello world. And once you deploy this in the blockchain, the transaction is deployed, and then you deploy this in the contract. You cannot change this contract anymore. And it will return you a smart contract address in which you can access this in basically any any place that you have access. And yep. Basically, considering smart contract best practice, because when you are doing a hello world, it's basically very simple. You don't need any complex coding need. But when you start to have more complex codes, more complex contracts, then you need to have in mind some best practices. It's important to consider also that blockchain is relatively new and most implementations are experimental. If we take a look on Bitcoin, for instance, it says that it is an experimental currency. And even though a lot of people put their money on it. And it's the mindset for developing for smart contracts need to be a little different from the traditional ones because basically now you cannot change. Once you deploy a smart contract, it will be there forever. And then before rolling out your smart contract, you need to have a very detailed analysis of your code and check whether it complies with your needs. Basically, the cost of failures can be high. The example here is the DAO, in which about $15 million US were lost in a very simple mistake in development. And you are still not immune to simple vulnerabilities in your contract. You can have failures in any sorts as in a regular coding. So best practices are essential, having in mind the security of the code, the efficiency of the code, and also the readability for those which are going to interact with your code. If we have in mind here the smart contract best practices, we have these 7 points being mainly being pointed out. The first one is to prepare for failure. You need to have in mind that this can fail at some point, and then you can define some of those circuit breakers that will mainly pause the execution of your contract. And basically, if something's going wrong, you can basically stop the execution of the contract. You can have a way in which you can limit the amount your contract is handling in a way that if something's going wrong, you would know you can have a control of your losses. And also an effective upgrade path for bug fixes and improvement. So having in mind that things can fail, and if fail, you have a way how to control the losses or even stop the execution of the smart contract. The second point here is to roll out carefully. Means that you need to test for complex contracts. And whenever you have new vector of attacks being discovered, you also need to check for those vectors in your contract. Bug bounties is something that was done for at least one of the startups that was created at UZH. Very important to having people trying to hack your contract, trying to find vulnerabilities and check whether it is safe or not. And basically rollout in phases is the last point here. One of the most important points here is to keep your contract simple. Do not try to reinvent the wheel. This goes for basically everything that you are coding. Ensure that it's simple. Keeping it modular, also using already written tools or code where it's possible. Do not try to, for instance, to have basically your own random number generator. This is something that basically you have things already being implemented on this sense. Do not try to reinvent and try to do a new one. Prefer clarity to performance whenever it's possible, and only use a blockchain for parts of your system that requires decentralization. So things that do not need to be decentralized, do not need to be on the smart contract, do not write on the smart contract, write on the centralized point in which you can call the smart contract later. So the main idea here is to keep things simple. Do not try to reinvent things that are already there. Do not try to put things that do not need to be decentralized inside the smart contract, because all of these can backfire later. Another point of recommendation here is to stay up to date, basically check versioning. The point that related with the rollout, carefully check new bugs, new vectors of attack when they are discovered. You need to check this as soon as they are discovered. Always keep this up to date, upgrade it to the latest version of any tool or library that you are using, and adopt new security techniques that appear to be useful, so to say. It's always important to visualize how your methods are being called externally, internally, and what is the effects on, for instance, the gas, execution of gas for solidity that those methods are requiring to execute. Be aware of the blockchain properties, what the blockchain can do, and what you are doing. Smart contracts are not supposed to be to execute very complex code, even though you can have complex contracts, but keep as simple as possible. Be extremely careful about external contract. For instance, contracts calling another contracts, and they will, if there is one of them being coded in a wrong way, they can run out of gas easily. Understand that your code is public, and this public readability, people can look at it, analyze it, and exploit the vulnerabilities of your code. Keep in mind gas costs and block gas limits. Timestamps are imprecise, and randomness is not trivial, for instance, in a blockchain. So basically know which the specific blockchain you are using and the properties that it offers for you to host your contract. And also you have these fundamental trade-offs. If you have a monolithic smart contracts, for instance, versus a modular one, or duplication versus reuse, duplication of code or reusing portion of codes, for instance. Or having a rigid, or rigid means that you cannot upgrade this contract for very simple functions, very simple things that you need to do, or one that you can upgrade. So basically, those are the fundamental best practice that you need to have in general, so to say. It's also very important that you use tools for security visualization before deploying your contracts, and those are one of the examples that we have here to have this visual information, visual help to check how your functions in your smart contract are being called. For instance, for Surya, SoGraph, you can generate a visualization of function control and highlight potential security vulnerabilities. So out of those automated tools that you can paste your smart contract, check how the functions are being called, potential vulnerabilities that you have in your code. So you have tools for that in this sense. So before rolling out the contract, it's always important to check to run your code on these tools, for instance. And moving here to these very specific examples of security examples, we have two famous examples. The first one is transactional ordering in a blockchain shop, and then the re-entry attack that I will show here. In this first one, we have that a customer, for instance, wants to buy something, but you have this method buy and the method set price. And here, if the user wants to buy something, you don't have nothing ensuring that when you call the function buy, you could change the price before the customer buying. So basically, before it buying, you could increase the price, and the user will overpay basically whatever he's buying. So how to solve that, for instance, it's to ensure that you have a conditional. For instance, if the user is going to buy something, for instance, the price 100, and then you could include this conditional if the desired price is the price. Having in mind that the contract is public, and you don't have a way how to ensure that the function set price is not going to be called after or before the set price. So you have this conditional inserted there that will ensure that the price that the customer wants to pay is the desired price. So this is a way how to cope with transaction order, and to avoid that whenever you're buying something, for instance, the store could increase the price and you are going to pay a higher price than the one you desired. So this is one example here of transaction order that, for instance, when the customer tried to buy and the contract owner tried to increase the price, for instance, to 120, this will fail because it's no longer the desired price. And this is one example of smart contract security. One very, very simple example of the transaction order. You don't have a way how to ensure the order of execution of transactions. And then you have the re-entrancy attacks. That was one type of attack that was explored in the DAO. And for here, we assume a good ATM and a bad ATM. In this good ATM, you have this method here, withdrawal, that basically checks the balance, transfer the funds, and updates the balance. I don't know if straightforward here, it's possible to see what is wrong in this method. Basically, assuming that we have, I'll get there. Basically, assuming that we have this bad ATM that has a method attack, it will call the withdrawal method there. And this will call the check balance, transfer funds, and then you have a method payable there that will call the withdrawal method again. And basically, the issue here is that you are transferring the funds before updating the balance. And this re-entrancy attacks means that if you have a malicious ATM, contract ATM, you could be doing a re-entrancy, calling again the transfer funds, the withdrawal function, until you can either run out of gas on the bad ATM, or you define a threshold for the amount of money that you want to take from the good ATM. And yeah, until the re-enters target it's reached, you can update the balance. So this was the example of the DAO, a very simple mistake on the line here. So basically you are transferring the funds before updating the balance. And this was exploited by one attacker, which could take around 50 million US dollars. And this can go until you run out of gas, until out of balance on the good ATM, or run out of gas on the bad ATM. So very simple things that you need to observe in the contract before rolling out the change. How you could solve that, for instance, you could have a definition of states. For instance, a state ready and pending. If you have here the function withdrawal being called, then you can set this to pending. And if you try to call it again, it will be pending and you cannot do anything until it's ready. So when you check the balances and transfer here, and you call the withdrawal again, then the ATM is not ready, it's pending. So it's a way that you can solve this kind of situation by having this state-based approach, which is still very simple. I basically lost here. When basically check and transfer funds, this will not work. It's a fairly simple approach. Only a small amount of gas is sent, and the receiver can only emit a single event at max. So those very simple examples here of security flaws that you can have in your smart contracts. So basically, having in mind the best practices is the best thing you can do. There is not also the regular software engineering best practices. You need always to keep up to date with the new attack vectors, new bugs, and having in mind those special peculiarities of coding smart contracts. You need to prepare for failure, roll out carefully, testing at each stage, having it simple, updated, and aware of each property of the blockchain that you are using. You can have also another issues, for instance, buffer overflow, for safe math. If you are doing a mathematical operation in your smart contract, this could run out of gas easily if you are not using it properly. Handling error and keeping always the best practices. So there are more recommendations here in this link. And with this, moving here forward with the discussion and considerations part, basically trying to do a summary of everything, an overview. We have, at least for public, Bitcoin, for instance, the sustainability issue, something that we as a community need to take a look. And one side effect that we are seeing is the proposal of many different consensus algorithms, trying to at least get close to the same level of trust that proof of work proposes, and the same level of trust. But this comes with a cost as well, on leaving the trust, accepting the reduced level of trust for some cases. One example here, in 2017, the energy consumption of Bitcoin alone was equal as the Iceland production. The issue with scalability in terms of transactions per second and volume of data. One real issue now that's the data produced by the blockchains, the cryptocurrencies, is higher than the capacity of hard drives being produced nowadays. I saw this graph. I don't have this graph here, but I saw the last Friday. And this is an issue. We are producing more data than our capacity to store, and not considering only the cryptocurrencies. So you have more blockchain projects than only cryptocurrencies. So this is really an issue, and it's not sustainable for a long term. You have the issue with standardized APIs as well for switching blockchains and blockchain-based apps, many economical effects, and those legal and regulative compliance issues. You basically need to be aware of the compliance on which country, which state, the different laws that you can have in the different regions that you are deploying, or you are going to have your code being executed. And if we try to map here the challenges with the different types of blockchains, basically in terms of scalability, data storage, sustainability, and identity management, we have that in public blockchain, this size, it's hard to be controlled. The data storage is not designed as a traditional database. You have high fees, and the storage is limited. It's one side effect is that we are seeing the increase of usage of off-chain storage approaches, in which you only store a hash on the blockchain and the data is stored off-chain. Sustainability with proof of work. Basically, you have no social benefit being out of this huge computational game to find a hash, those partial hash collisions. On the identity management, you have pseudo-anonymity, you have the accounts, hashes identifying persons. It's hard to link with physical users. On a public permissioned, considering scalability, you have only selected nodes, so you have more control over the size. You can scale a bit more. In a public permissioned, you have no writers, no fees, and no size limit, so you can actually change a lot in your blockchain on a public permissioned one. For instance, you can have proof of authority or PBFT. here, and data is supposed to be visible, ensuring integrity, only for those participants. In a private permissioned, here, you have designed for a specific use case in which you can close the readability and keep open for those who are participating in the blockchain. You have low fees, partial size. You can also have proof of stake or proof of work, PBFT, and you know basically the participants of your blockchain. A private permission is the case for a traditional database in which you can control the size, you know the writers, you have different types of consensus mechanism that is not proof of work, and you know the participants, so it is a trusted environment. Also, concerning standardization and trust on economics and regulations, basically summarizing here for the public permissioned ones, you have no clear regulations, so it's in a gray area. Also for the public permissioned, and only for those in which you can control more or less where it's going to be executed, or you know the participants, you have more control over the blockchain. Moving forward here to the risks, the true semantics of what is stored in the blockchain depends on the input received. So essentially, it's a structure in which you store data. But the data itself, it's stored by someone, some application, and you don't have how to ensure that. Security, privacy, and reliability depends on basically the cryptographic mechanism that we have available as of today. If all of these are broken, then all of the blockchain security is also broken. But we also know that if all of these are broken, then perhaps the blockchain is the least of the problems that we have. But it's something also to have in mind for the security of the algorithm that you are using. Also GDPR, we know by a fact that in some cases not even a hash identifying a data is accepted by some companies. So what is possible to do? When you store something is immutable, you cannot change. In some cases, not even having a hash is acceptable. So it's a challenge. And economical and legal risks that we already spoken, all the fraudulent activities involving cryptocurrencies, the hype, people exploiting the hype to make a profit, and the volatility of those coins, all of those are risks. Here more for the investor perspective. And to come to a conclusion here of the talk, the blockchains do show an evolution of linked lists. However, we are exaggerating the processing demands, especially proof of work, because now we need to have this very expensive election process to decide which is the next block. But in the meanwhile, we ensure immutability. The security of blockchains basically relies on the security that we have today. We don't know, for instance, the impact of quantum computing at all. And if those algorithms are broken, then all the security behind blockchain is also broken. And to conclude here, we have that blockchains are not a revolution, but an evolution of things that we have as of today. We don't see, as of today, blockchain completely replacing a system that we have today. Blockchains only help to improve, in some cases, some particular cases, the system that we have as of today, but not replacing. So it's an evolution. So, yep, has not been replaced, and only improving. And with this, I would like to thank you for the talk. That's it. If you have questions.
Yeah, hi.
Hi.
So in one of your slides, you mentioned that smart contracts, once deployed, are not possible to change.
Mm-hmm.
So what does this really mean? Because the logic that is behind any use case may require an change and upgrade for sure.
You basically predict the state of the smart contract,
Sorry?
But you basically update the state of the smart contract. For Ethereum, for instance, it uses a different type of tree, those Patrician Merkle trees, in which you can update the state of the smart contract. So if you have a variable, you can always be updating the state of the blockchain. But then the previous states are also recorded. And once you deploy the code itself, you cannot change the code, how it is. The functions, this is not possible to be changed.
But that is what my query is. The contract is basically the business logic, or the logic that is behind any project or a use case. So it may anytime be require a change in the logic, because the smart contract is generally agreed between the participants and then deployed. But the participants themselves may later on, decide to change the logic. So there should be a mechanism for an upgrade or change in the smart contracts, isn't it?
Yep, that's true. Things change, the business evolve, and then for these cases, a new contract has to be deployed. And that's one of the reasons why we have all those best practices before rolling out the contract. You need to check if all the parties involved are okay with the terms of the contract, if there are no vulnerabilities. Basically, you have to check everything before deploying the contract. If something evolves, it's a change that you need to basically to upgrade on the decentralized apps, check with all the community. If it's public, if it's a permissioned, you have to check with all the participants and roll out a new version of your contract.
Okay. And another thing was, another of your slide, you said that smart contracts may reside in transactions.
Reside?
Yeah, one of the slides said that. So, didn't get this. The smart contracts is available with all the nodes that are, all the participants that will execute, or they reside in the transaction?
I was referring to the states. Basically, yeah, they can change the state of the variables. So, in this sense.
Okay.
Sorry if it was not.
Thank you.
Thank you. Yeah, I have a question about. So it might be related to the question asked by the lady there. So, what if the contract has been there for a while? Lots of people are using it, and there are some stakes. Some people have great stakes in that smart contract, and if that logic should change somewhat, like let's say some product has been sold like a $10 per item, but now it will be sold like a $15 per item, for instance. If that happens, then in your opinion, what seems to be the best action to take if I want to alter the already deployed smart contract?
For instance, in this case, if you want, you need to have in mind in the design before rolling out the contract, the variables. And you also need to control who is entitled to change those variables. For instance, the price, you can have only the contract owner defining the price. And once you have this price defined, everyone that interacts with this contract should be able to get this price and check if this, and then decide if this makes sense or not. But having a variable, very simple variable with getter and setter would be a way. So it's on the design part. And if this changes, then only the contract owner can change.
Kind of a little bit sounds like we are kind of defeating the purpose of decentralizing if in that case only the contract owner is capable of altering those crucial variables or mechanisms. Like, what will you say about that one?
I would say that it's still decentralized, and since everyone can see and can agree on it, so it's not something hidden. Only one party has access to how things are implemented on this contract, so everyone can actually see the state of the variable. Everyone can see the price and see how the methods inside the function are implemented. So it's still completely open and transparent to everyone. But it's regular. If you have, for instance, a store there, you can define the price of the things that you have in the contract, for instance.
Thank you.
Just simple questions.
Yep.
Okay. Usually, when you classify the blockchains, for you give an example for quaternion. So among them, the private permissions, based on the you are talking, the private permissions. Sometimes it is the
private permissioned.
Yeah, permission. That is just a simple database is better than the private permission. You classify that one. You mentioned that one.
Which slide?
Not, but
I'm not sure if I can understand. If the private permissioned is equal to the private permissionless, in which aspect?
no. Private permission is just a simple database, one single database. You mentioned that one. Based on your talk,
okay. Yeah, it could be replaced by databases.
Yeah. So based on that explanations, so but usually when we classify the blockchain for cases, so can you give a simple example, simple use cases for private permissions? For it's very effective, just simple by using the single database.
For instance, there are a lot of use cases that actually you have to trust in some entity, and it falls in one of those cases that we saw in the methodology. If you trust one entity, then you don't need blockchain at all. But we often see this being pushed, mostly because of the hype in the blockchain. There's a huge hype and people trying really to sell blockchain-based products. And we do see that often you have a very high level of centralization in one of the nodes, and you start to close the permission, the read and writing access, and centralize at the same time, and then this is no longer a blockchain case. It's something that seems like the blockchain was trying to insert it there. To be very specific, we could find some cases on supply chain. I'm not name of project or company, but you can find in cases of the supply chain, because supply chains, basically you cannot have completely open to everyone in the world. And you also need to close those to those who are entitled to write. And on this case, if you start to centralize things a bit, then it would be better to use a distributed database. So for the supply chain, for instance, for some cases, not all of them, you have those cases that they use a private permissioned one.
Could you tell us your thoughts on how to solve the scalability problem? Like, what are the most promising approaches to increase the transaction throughput?
That's highly dependent on the application, of course, and basically replacing the consensus algorithm. That would say, but you need to take take in consideration what are the application needs, what is the community involved, and the type of deployment that you have. It's heavily reliant on the consensus that you are using. If you can use PBFT, for instance, you can achieve a higher throughput in terms of transactions per second than proof of work. But to increase that specifically, you could also have the sharding approach, which is being used with witnesses, and then this could be a way to try to increase the number of transactions per second, but heavily depends on who you can trust right now to have your transactions being deployed. If you have the election process for public permissionless cases, then proof of work is still the case to be used because of the trust mainly.
Thank you.
Okay, I guess there are no more questions. So I'd like to thank the tutorial speaker, Bruno, the first one. Thank you very much.
Thank you. Sir James.